learning model is based out of the data you pass to algorithm. So even if you pass a different data to same algorithm, it's a different model altogether. So either if the data is different or algorithm is different, they will be a different model. So we all know that the model performance is based on the performance of algorithm and the performance of data. In our last webinar, we touched upon the method to improve machine learning model. You can see that recording on our YouTube channel, Celestate YouTube channel. So we talk about in that webinar about different methods which can help you to improve your machine learning model. So adding more data, cleaning the data, selecting right machine learning algorithm, hyperparameter tuning, feature engineering, using ensembles, and the cross validation. So we touched upon that. Today's topic is once you optimize your algorithm, and once you fine tune your algorithm and you find a right algorithm for your data which is able to predict your data properly or able to fit your data properly with the algorithm, you want to know what is the performance of your algorithm now. So how your algorithm is able to perform on the test data or a new data. So this is a generic procedure we use. We get some label data. We split that data into training and test set. Now there is one more method which is cross validation, where we further break training set into different subsets and then train our model on different subset to reduce the overfitting problem. But we will not touch upon that here. Then once we pass our data to our model, learning model, which is here, then our model learns from the data. So our model captures the features or different characteristics of our data, and then a learned model comes out. Then the model which is learned or which has been fit using our learning data or test training data, we pass our test data into that model, and then we see how accurately our model is able to predict the test data set, and which is and then we come out with the accuracy estimate. So there are different methods to test this accuracy estimate based on the characteristic of the algorithm and the kind of problem you are trying to solve. So today we will talk about only predictive models. So models like classification models and regression models. For classification models, the evaluation metrics are log loss, accuracy, AUC, lift gain chart, confusion metrics, and some more, but these are the most popular. For regression models, we have RMSE, MAE, MPD, MPE, R square, and some more, but these four are very popular and most popular algorithms or most popular metrics to evaluate a regression model. So we will not talk about so you can see that these classification regression both are part of your supervised learning models. So we will not talk about unsupervised learning model, because to evaluate our metrics, we need some label data or some dependent variable based on which you can evaluate how many data were expected to predict right, and how many your algorithm was able to, or your model was able to predict. So because you have some benchmark to judge your algorithm, so it's easier to predict the errors or the performance of your model if you're talking about the supervised learning model. For unsupervised learning model, because we don't have anything to any benchmark, because we don't have labeled data, it's very difficult. So we will not talk about that today. Okay, so now we talk about how the machine learning deployment. So actually, you build a model. So how the machine learning models are deployed and built. So we will touch upon that. So there are two stages of a machine learning model. One is the prototyping, and one is deployment. So in prototyping, we have some historical data with us. Using that data, we train our model, and then we evaluate our model or validate our model. And after that, we deploy our model onto the deploy our model for the live data, and then we keep on testing our data. So it's not about that you build a model and you deploy a model, because we have already seen that our model changes with the data, right? So it's not something similar to a traditional a computer program that you build a program and you deploy it. Because the data changes so rapidly, your scenario changes so rapidly that your model will not work after 5 or 6 months time. So you need to evaluate your model continuously, that still my model is good enough to handle the new data, or is it not? If your model is not good enough, if you find some deviation from the model, you have to retain your model. So we can take an example of say gadgets, right? So today you build a model which is able to learn that if I pass some characteristic of a gadget, like the hardware configuration of a gadget, its display size, its video capturing capability, its RAM, its processing power, what should be the cost of the gadget? So I build a model based on these parameters, which is estimating the cost of my gadgets. But tomorrow, after 6 months or 1 year time, if the RAM generally doubles. So today I'm talking about gadgets which are having generally 1 to 2 GB of RAM. But in after 1 or 2 years, if the model is having 4 GB or 6 GB RAM, the data is having 4 or 6 GB RAM, my model is not going to work. So it will deviate from the error matrix. So I have to retrain my model. Similarly with the prediction model, which are predicting the news, right? So news topic changes rapidly. Today something is very hot, and tomorrow something else is very hot. So to handle all these rapid changing in data, we need to train our model continuously. So this data changing and our model tuning is called distribution drift. So if there is some drift in the data, the model will also not perform well, and based on that you have to again retrain your model and deploy the new model onto the live data. So model evaluation matrix is used to access the goodness fit between model and data. So we already talk about that the model is a combination of algorithm and data. So our model is how well our model is accommodate all the features from the data. It's goodness of it. To compare different model, right? So the error metrics can help, or evaluation metrics can help you to. So you have some data, you build that data, you train your model using that data, and your model perform quite well, but you are not satisfied. So you build one more model with some more different data, or fine tuning the algorithm, or a different algorithm altogether, and then you can again evaluate that model on the metrics, and then if the second model is performing better, you will select that model. So metrics can also help you to evaluate two different model, or comparing two different models. A similar thing is with predicting how your model is performing. So you deploy a model today and you found that my model is accuracy is 84%, and tomorrow, after 6 months, you start seeing that my model accuracy is decreasing. So from 84% now it's performing 82% or 80% or 75%. So it gives an indication to you that your model is not able to predict the new data properly. So it's a time to change your model. So as we discussed that once you deploy a model, it's not a one-time activity. You need to again, keep on building your model on new data, or retraining your model on new data and deploying it again. So these error metrics can help you to evaluate your models, and then taking the appropriate action. Okay. So if you talk about classification models, so you all know in classification, our responsibility or our main goal is to classify our data into two different categories. So if we are classifying a data into two categories, okay, we got some data and we want to categorize whether this student will pass or fail. It's a binary classification, because we have two buckets. But if there are multiple buckets, there are 5-6 classes that you have some data. Now you have to define that this is a horse, or a donkey, or a cat, or dog, or multiple categories. Then it's a multi-class classification. So here is an example of binary classification. So the confusion matrix is the core of all the evaluation metrics we use we use in classification problems. So, or we use to evaluate a classification model. So if you see here, there is a model which is depicted by a red line, and I have data, two class of data. One is z dot, one is blue dot, and one is z star. So my model classify this data, I pretty well, that upper the data above this line is classified as one, or some one class, and the data below this as a second class. But you can see there are some anomalies also, right? So this red star is in a wrong bucket, right? And all these three blue dots are in a wrong bucket. So we use a classification matrix to find out, how well our model was able to classify the data we passed to that model. So if you see that this model is classified the data pretty well, but still there are some glitches. Four data points, my model is not able to classify properly. So to define this problem, there is a term called confusion matrix. So let's go in detail, what confusion matrix is. So confusion matrix is a matrix which keep your data in four different buckets. So if you see that your actual positive or your actual data for blue, so let's say that we consider blue as a positive here. So the actual blue points were 20. Your model predicted 17 point right, and 3 points it was not able to predict right. So these were the actual data, 20. You can see, and the prediction was 17 you predicted as in the upper bucket, and 3 you predicted in the lower bucket, right? Similarly with this red star data, 1 we predicted in the upper bucket, which is wrong because it should come down, and 9 we predicted into the lower bucket. So to define these all these four buckets, we have different nomenclature. So true positive or TPs, true positive are the cases when the actual class of the data was 1 true and the prediction was also true. So if the data was actually true and we also predicted true, we call it true positive. True negative is data was false and we also predicted false. So don't get confused by this false or true. These are the nomenclature, but the objective is to define that, if the data which is associated with the bucket 1 or the category 1 is defined properly, it's a true positive. The category 2 is a true negative. False positive is cases when the actual class of the data point was 0, so or false. So actual class was false, so we call it false, but we predicted it's true. So then we predicted it's true, but it was false, then we call it false positive. False is because the model has predicted incorrectly, and positive because the class predicted was positive. So it was actually negative, but we predicted this for positive. So second term F in FP is what we predicted, and the first term F is it was true or false. So we predicted positive, but it was false. It is false positive. Similarly with false negative, we predicted as negative, but it is false, right? So it's false negative. So the ideal scenario is the ideal model is that if we are able to predict, build a model which is able to predict our positive and negative data correctly. So that's a 100% fit model, 100% accurate model. But that is that never happens, right? In a real scenario. So now this confusion matrix help us, how many right prediction we have done. So 2017 plus 9 are our right predictions, and 3 and 1, 4 are our wrong predictions. So we will see that all the classification metrics we will see in coming slides are based on the confusion metrics. So we will just optimize confusion metrics. We will drive more formulas out of these metrics to define those metrics, right? So the simplest metrics is accuracy. So accuracy only predict how many right prediction you have done and what is the total prediction. So if you see that 26 of your predictions were right and out of 30. So if you so it says that my model is accuracy is 86% because I predicted 17 plus 9 26 out of 30. So my accuracy is 86%. But the accuracy is very basic metrics. There are some cases where your accuracy will not give you not tell you the actual picture. It will not go into the details of your model performance. So what are those cases? the one is multi-class classification. If you have more than two classes, so here we just discuss about the binary classification. But if you have more than two classes, so I want to predict that I have a box of red, blue, and green balls, and I want to classify properly that whether this ball is red, green, or blue. So now we have three categories or three of data. So it's not a binary; it's a multi-class classification data. So similarly, if I want to separate out pears, mangoes, and apple, or pears, oranges, and apples, it's a multi-class classification because now I have three classes. So in case of multi-class classification, your accuracy will not be able to tell. That it will tell you the accuracy of the prediction, but whether you are able to classify every class properly, it will not. So we will see in next slide. Skewed data if is imbalance. So especially in the case of say disease diagnostic. So maybe we have 10,000 cases or 10,000 samples of our population, and generally we know that diseases are. So if we talk about any major disease like cancer, right? So if 5% of people are affected by the disease, our data is imbalanced because 95% of cases are one side, which is not affected by the disease, and 5% are other side, which is defected. So this is the imbalanced data. So in this case, or we can say it's a skewed data. In this case, the accuracy will not give you the right parameter. Accuracy is not able to give you the right metrics. The cost of misclassification, and sometimes the cost of misclassification, like if you classify, if you predict someone who is having cancer, that he doesn't have a cancer, or the vice versa, then the cost is different. So we will touch upon that in the next slide. So let's move to next slide. So okay, you can see that the first problem is multi-class classification. You can see that class A, our model was able to predict class A correctly, right? 15 out of 15. Similarly, class 2 we are not able to predict correctly. 10 plus 5. So the accuracy of a class 2 by our model is just 66%. And if you see for class 3, it's just around 50%. So if I just take an average 15 plus 10 plus 8, which comes to 33% out of 45, the model says my model is 66% accurate. But for every class is performing differently. For class 1 is 100% accurate, for class 2 is 66% accurate, and for class 3 is 50% accurate. So this thing you are not able to capture with accuracy. So there are some advanced metrics which you will see, which can be used to capture this data. Similarly, the second point is skewed data. So if 95% of out of 100 samples, if you feel that 95% of our cancer are right healthy people and 5% of people are only ill, then this is not a balanced data, because it's tilted towards healthy people, right? So accuracy will not be able to tell you the right metrics about both the classes, healthy and unhealthy. The third point is different misclassification cost. So you see that in the third matrix, actual cases of ill people were 5, right? You predicted 4 are ill, and you predicted 1 is not ill, right? Similarly, you predicted that the model predicted 92 of are healthy and 3 are not healthy. But this 3 is not that dangerous if we compare it with this 1, because the 1 depict that someone who is having cancer, the doctor or your model told him that you don't have any cancer, right? So because now he can be free and he will not go for any treatment, it's more risky for him. Instead of these 3 where someone is not having cancer or your model told him that you have a cancer, because still he can go for some initial treatment or second opinion, and he can find that that I don't have a cancer, but it's not going to affect on it's not going to cost him his life. But this one where he's having cancer and you told him that you don't have a cancer, it can cost someone's life, because now he will feel that he will not go for treatment, right? So this wrong data and this wrong prediction here and this wrong prediction here, though they are of wrong prediction for different class, but their cost is different. So this your accuracy algorithm will not be able to tell this, right? So now we will talk about some advanced algorithm which can capture all these deep level of understanding about different classes. So the another algorithm which is better than accuracy is precision and recall. So precision tells what percentage of our data of our true predictions are actually true. So precision is TP by TP plus FP. So actually, so you predicted something, right? TP plus FP, and precision is how many you predicted something true. Like so, TP plus FP is your prediction is true, but out of that, how many were actual true? So precision tells that. So if you see this case, our precision is 5% because we only predicted 5% of cases are true, right? So this precision is 5%. The recall is on the other hand, how many you missed. So actually, how many were true, and you missed the false negative. So what percentage you actually were able to predict? This is called recall. So recall here is 5%. So precision tells about even if you capture only one spam mail, right? So 99 were not spam in your case, and one was spam, and you captured it correctly. Your precision is 100%. So precision tells how many right prediction you were able to capture by your model. At the other hand, recall is something how many prediction you could not capture. So it all about false negative. Recall is more about capturing all cases that is spam with the answer is spam. So if we simply always say every case is spam, we have 100% recall, right? So spam is something, recall is something which you are not able to capture. So now we need to strike a balance between precision and recall, because these two numbers, every model is a balance. If you go for more precision, the recall will be lower. If you go for more less precision, recall will be higher. So now our requirement is to strike a balance between precision and recall. So F1 score is a matrix which gives you that opportunity. So what F1 does, it gives you a single matrix which can give you a number which is having essence from precision and recall both. So one thing can be you have some precision, you have some recall, and you take an average out of it. So if you see our earlier case, our precision was 5%, our recall was 100%. If you take a mean or average, it was 52%, which says that our model is quite good. It's better than tossing a coin, because tossing a coin you have 50% probability, but our model is giving you 52% probability. But if you see, our model is horrible, because you see that true positive was only 5, and actually it brings 95% of people. So which were actually healthy, and you predicted that those were sick. So our model is pathetic. But if we take a arithmetic mean of precision and recall, it gives you 52% of value, which is not good. 52% is still suggested your model is better than tossing a coin, but my model is horrible. So for that we use a harmonic mean, which is called F1 score. So the harmonic mean formula is 2 into precision recall by precision plus recall. So if you use F1 score here, your model accuracy is 9.5%. So which is right, because your model is horrible, right? Because 95% of data which you are actually healthy, and you predicted them ill. So your model is a horrible model. So though the mean and the precision recall are not able to capture it properly, but this F1 score is able to capture it properly. Okay. But so lift and gain charts. So lift and gain charts are another metrics which commonly used for marketing campaigns. So if a business want to launch a marketing campaign to attract more customer, they feel that their accuracy rate is 20%. So they sent a mailer to one lakh customers, or and they realized that 20% is the accuracy rate. So they expected that response rate is will be 2000, sorry 20,000. But that's a generic data. So to get a 20,000 data, it's a 50% of the probability is 0.5, or probability is it's just about tossing a coin. So for that you build a model. So your model can identify those people who are most likely to click your ad, or who are most likely to respond to your data. So how this can help, because once you run a marketing campaign, it needs energy and time both, because you need to build mailers and send to those people. And if it's a blind hit, you never know. You want a specific customers, you want a name of the specific customers who are actually more likely to click your ad, or likely to respond to your model. So for that you build a model. But how you will check your model is accurately? Because even if you with 20% of accuracy rate, even without a model, you expect that 20,000 people are going to respond back. But can your model help you to understand better? You build a model, your model suggested, okay, these are the customers. If you send mailer to these only customers, they are more likely to respond back. So your model suggested that. But now how you will test it? How you will measure that my model is better than tossing a coin, or it's giving me some insights which will help me to save some time and money, and I can only send data or send mailers to customers who are most likely to respond on it. So you can see here this table, that if you, without a model, if you send 10,000 customers, the first 10,000 customers, the model, the mailer, and you felt that 20% will respond. You expect that 2,000 will respond. But with your model suggested these are the customers which are most likely to respond. You were able to get 6,000 out of those 10,000. Now next 10,000 you got 4,000 more. Next 10,000 you got 3,000 more. But as you know that because first you filter out, so how you will get this number. So actually how your model tells you that these are the most probable customer. So your model suggests you that the probability of this customer of responding back or responding positively on your mailer is 80% or 90%. So first you only choose those customer where your model suggests the probability is higher, and you will send the mailer to those customers. Now you send mailer to those customer, and after that there are a customer which are in the bucket of 80 to 70%. You will send them. Then the customer which are 60 to 50%. So this lift and gain chart can help you. So you can see that this pink line is something which is a common line. So which only tells that if without a model, if you send the data to any customer blindly, that the probability rate of them to responding is this 2,000 for every customer. So for these customers, these guys will respond, and for further they will respond. But with this chart, now you can accurately predict that how many guys can respond to your data. So with this, without a model, 2,000 were able to respond, expected to respond. But here with this data, 6,000 are expected to actually responded. So this chart actually tells you that how accurate your model is. So initially, if you see that after 40% contact, you are able to tap 80% of your customer. Without this chart, you are able to only tap 40% of your customer. But with this model, you are able to tap 80% of customer, and with the accuracy of 60%. After 60% of contact, after contacting 60% of your customer, here actually you were able to contact. You get 90% of response. So this chart helps you to identify that how accurate your model is. Similarly, this is a gain chart, and similarly on this data, based on this data, we build a lift chart. So these gain and lift chart can help you to tell that how is the performance of your model. So if I see that this chart is so that the area between this chart is also very important. If this chart is more convex, in this shape, it means our model is better, because then after just sending 20% of data, we were able to tap 90% of customers. So the lift and gain chart help you to estimate your model, the performance of your model. Similarly, there is a chart which is called ROC curve. So we know that ROC curve can help you that so suppose how your model predict the probability. So the model predict the probability between 0 to 1. So that probability of this guy going for loan is 7.7, and then you define a threshold that if the probability is higher than 0.5, I will keep it as a true case. If the probability is less than 0.5, I will keep it as a false case. So you define it into two buckets because it's a binary classification if you are using. But that is not a case always, because the probability change, you have to change your threshold based on the requirements you have. So but the confusion matrix we have seen here doesn't tell you about the sorry, okay, where it is. Yeah. So the confusion matrix here doesn't tell you about the probability of your outcome. It only tells you the buckets, 1 or 0. So it hides the probability details, that if the probability was 0.85 or 0.7 or 0.6. So if you get any probability more than 0.51 to 1, you are going to put it into bucket TP, and the probability less than 0.5 to 0 to 0.5, you are going to put it into bucket TN. So this is not going to help you in some cases. That's why this ROC curve really helps. ROC curve, actually what happens, it create a curve between your wrong prediction and right prediction, and then it helps you to identify that how accurately your model was able to predict that value. So the one more thing we already discussed, that always false positive and false negative are having different costs. Here we have seen that, right? So ROC curve also help you to build a right threshold to keep your costs low. So one example can be a fraud detection. So suppose you miss a fraud case, right? You are not able to capture. So you create a threshold which is not able to capture a fraud case, right? So maybe that the fraud case was 0.4 and you put it into that this is not a fraud 0 bucket, but actually it was a true bucket. The average, and if you miss a fraud case, actually it costs your bank $1,000. But if a case which is not fraud, and if you predict as a fraud, the initial investigation and checking can cost you $100 price. So you want to keep your threshold, so all your FN case, your false negative case, should not be less than 10% of false positive case. Because if you miss a false positive case, it's going to affect your bank $10,000, and if you miss a FN case, false negative case, it's going to impact your bank $1,000. So you have to strike a balance between these two values, right? So how you will strike a balance? You have to change your thresholds. That you will realize that 0.5 is not a threshold which is appropriate, because with the 0.5 threshold, I am getting false negative and false positive case equally, but the cost of false negative is much higher. So you want to change the threshold. So maybe you will want that 0.4 will be my threshold, so that my false positive case are always higher to false negative case, and I'll not suffer the loss of money. So this ROC curve will really help you to do that. So how ROC curve is drawn? So the ROC curve is a curve between your false positive rate and the true positive rate. So the true positive rate are also called sensitivity. They are TP, true positive by true positive plus false negative. So this is the actual truths are your the true positive by actual true are your TPR case or sensitivity case. Similarly, the specificity case. But we draw this graph between TPR and FPR. FPR is 1 minus TNR or 1 minus specificity, and this graph is built. So we take all the thresholds. So maybe we take the threshold value of 0.001, and on 1.001 threshold value, we draw this case that we check, what is the false positive rate and what is the true positive rate, and we build a point. Similarly, for all these small threshold values, we build this graph, and this graph is in this shape. So if you see that ROC curve graph, because this is a graph, because the TPR value and FPR value are not going to be larger than 1, they are in the bucket of 0 to 1. So this graph really helps you to build that. So this curve actually is a percentage of true values and the detected accuracy, and the percentage of negative values missed by the classifier. So this is something between that, and this graph can help what should be the threshold. So maybe if we keep that, so don't get confused. These are actually not one graph. So these blue, red, and green are 3 different graphs for 3 different models. And why I put these 3 graphs here, that because this can also tell you that which is the best model. So we will see in the next screen which is the best model, because the ROC curve not only helps you to define your different thresholds, but also can help you to identify what is the accuracy of your model. So suppose you realize that I want to keep false positive and true positive rate both low. So you can have your threshold somewhere here. So maybe this is 0.2. You want to keep your false positive and true positive rates both high. So you want to have a threshold somewhere here, which is 0.8. So this really helps you to draw a graph and identify which is the right point for you to decide the threshold. So you can strike a balance between your false positive, true positive, false negative, and true negative rates, right? So okay, so we discussed that here we discuss about how this graph can help you to define the threshold. The other point is AUC. AUC is area under the curve. The AUC can help you if you draw this graph. This is the same graph between FPR and TPR rates. The AUC curve can help you to define your model performance. So this is the standard line, red line, which is a line for random selection or 0.5% of probability, and this is our model line, the blue line. So all the area between this blue line and this red line is called the AUC, area under the curve. So different. So if you see here, right, the green area of under the curve for green chart is lesser than the red, and then the blue. The blue is the highest. So in this case, my blue model is the best model, because the area under the blue model is highest. The area under the red model is better than green, but not is less than blue, and similarly the green one. So the a good ROC curve has a lot of space under it, right? So if the good ROC curve is somewhere this triangle shape, but this is not possible because we know that our model cannot be 100% accurate. A bad ROC curve is somewhere between this green line, or where the area is lesser between this red line and the blue line. So that curve is not good. So so the higher the area, the better the curve is. These are some metrics. If your AUC is more than 0.9 to 1, it's the best model. 0.8 to 0.9 is a good model. 0.7 to 0.8 is a fair model. So AUC can also help you to analyze your model, right? So the log loss matrix is also similar to AUC, which can help you to identify the problems or the percentage or the error of your model. So I think most of you have heard about Kaggle, right? So once you submit your model to Kaggle, actually Kaggle use log loss metrics to measure the accuracy of your model. So log loss, we also call it the cross entropy or cost function in gradient descent and neural networks. So all these are same. So they can help you to how good your model is and how bad your model is. So log loss is one more matrix. Now we come to the regression matrix. So the regression task is not about classifying 2 different categories. It's about predicting the continuous number. So if I give you a data of house price and house area, you build a model, and if I give you one more, if I want you to predict, I give you some area of a flat, and I predict, what will be the price. Your model will be able to tell me that what will be the price. So mostly all the metrics for regression are similar to each other, because they are just measuring the actual value and the predicted value, and the equivalent distance between these two values. So most are same, but based on your error rate, the number of anomalies in your data, what you are actually trying to do, we the matrix changes. So, but there is very little change between all these metrics. So we will just explore few of them. So the most popular matrix is RMSE. So you can see this is your model, right? And you predicted something. This is red line is your model, and these are the points which. So the blue points here are what the actual values of the data. So suppose uh, I ask you that, what will be the actual value of this house if I give you the area. You predicted something which is falling on the red line here. So you predicted this way. This is the price of this flat, but the actual price was here, the blue point. So this difference between these blue points is the error of your model. So if I add all these errors, positive, which above is positive, and low, which are behind the line, are negative. So if I add all these errors, this will give the error of my model for that data, for that particular data. So in RMSE, what we do, we take the predicted value, which are on this red line, the actual value, which are these blue points. We subtract the actual from the predicted, take a square of that, and then we take a square root, and then we divide by all the values. So if there are 30 points, we will take the predicted and actual values of all 30 points, take a square of that, divided by 30, because the points are 30, and take the square root of that. So this is a basic algorithm or basic metrics for to predict the linear the regression model, different regression model. So the RMSE is, if the RMSE is near, if you take a RMSE of your test set and the RMSE of training set, right? Because you train your model on your training set. If they are near, or they are almost near to each other, we can predict our good model is good, because our model was able to predict our test data properly. If the RMSE on test set is higher than RMSE on training set, if there is a difference, our model overfit. So our model was not fit properly, and we need to either fine tune our model, or we need to pass more data to our model to learn correctly. There are some cases where RMSE is not a preferable model. So we use RMSE is not a preferable matrix. We use mean absolute error, MAE. This metric takes an average absolute difference between your prediction and the actual values. So instead of squaring, it just take the average, and it doesn't take, because RMSE consider the values which are above the model as positive, the difference, and the lower as a negative. This model take the absolute value. It doesn't take the sign. It doesn't take care of sign, and it only takes the absolute value. The median is, if you have some anomalies in the data, or your data is skewed, then you feel that there are some data which are away from other data, or some anomalies values. In this case, the mean will not help you, so we take a median difference of the of actual and predicted values. So this is called a median absolute deviation. Similar is mean. If we want to take a deviation or measure deviation instead of real values into the percentage, then we use MPE model. So all these models, as I said, are almost same, but based on your requirement or your case, you can select the right model for you. So now I think I am done with all the metrics which are commonly used in predicting classification and linear regression models. I just want you to show some program. So if you want to predict the accuracy, I have a data set of patient data set. which will tell you how many patients are actually having disease and how many are not. For that, we are using this linear logistic regression to classify them into the categories. It's a binary classification, and then we are evaluating our prediction. So here, we are using accuracy. So we talk about accuracy as our model. So let me run this code. So you can see that for our model, the accuracy is 76%. But as I said, if our data is skewed, the accuracy doesn't tell that uh, which whether it's able to predict the ill people and healthy people category equally or not. So maybe it's able to tell you that ill people category properly, able to identify or predict all the ill people properly, but not the healthy people properly, right? So it's not a right way. So then we discussed that we will use confusion matrix. So this is a confusion matrix. Let me run this code also. Okay. So now it says that this is confusion matrix. So we can see that 96%, 96 of the ill people it was able to detect properly, but it failed. Similarly, so here this category is better, because 96%, 96 out of 104 it was able to detect. But if you see that the lower one, which were actual healthy people, it was only able to predict 25% properly, right? Accurately, because 23 out of 27. So there was something which was accuracy not able to tell you, but this confusion matrix was able to give you the right picture that our model is able to predict one category properly, but not the other one. So we need to fine tune our model. But still, this model is not able to give you the actual score of your data, right? So for that, we use precision recall. So let me run it. Discuss. So precision and recall can give you that 80% of precision, 80% of recall, and your F1 score was 79%. So you can use this matrix if you want to go more detail. So this program I used skitlearn libraries, and you can also use that, and it's very simple. These are simple programs to run. Similarly, the AUC can help you to, again, if I run it, AUC can give you how what is the area under your curve. So you can see the 85, 82% is the area under your curve for AUC diagram. It means the model is quite good. Logarithm loss can also we can run if you want. So logarithm loss can also be used. So logarithm loss for this model is minus 0.49. So you can compare it with other models, and you can identify which is the best model. Similarly with RMSE and RMAD. So let me run the RMSE program, which is a linear regression error matrix. Okay, so RMSE give you. So why this error is high? Because RMSE give you on the real value. So we are predicting our price. Price is in dollars, millions of dollars. So that's why this value is really high. But don't worry with it, because you will use relative values to compare. So don't carry. So it's not going to affect your errors if you use a lower value. So if I, instead of dollars, if I deal in millions of dollars, this value will be quite lesser. So these are the programs, and I think I'm done with my. I'm done for today's webinar. So if you have any questions, and if you are still able to post some queries, you can, or if you, Vishal, can unmute participants, so if they can ask some question. Vishal, can you unmute the participants audience so they can ask some question if they have?
So I suggest if they are able to post questions on meetup.com, that will help. Or if somebody raises hand, probably we may be able to see.
Okay. So guys, I really I understand this is a very difficult topic, and I also got confused once I started metrics few years ago, and it's a pretty lengthy topic or heavy topic uh, to be taught or to be understand in just 45 minutes of time. But my objective was just to give you the introduction of different algorithms. So if you want, you can go on and search on net. And if you still have problems, you can drop some mails, or if you still have some doubts, drop mails to us, or put it on Meetup site, and we will try to answer your questions. Right?
So somebody is saying that I think Mohit is asking if we can give you the contact details. You can send your queries at contact@cellstrat.com and we will respond it there. Slides. This webinar is being recorded, so it will be loaded on YouTube channel, Cellstrat YouTube channel, and also we'll be sending you a newsletter around Monday or Tuesday. Then you will be able to see the webinar recording on the site. So again, Cellstrat is a YouTube channel name.
So one more advice for the audience, because I could see that there are few who are the first comers. If you don't have any idea about different machine learning models, you will really find it hard to understand this concept today. So I'll suggest you that you go and first read our two webinars on machine learning models, classification, regression, and then our last webinar on how to optimize the machine learning model. After that, you will find that this topic will you will find more easier to understand, because if you are a newcomer and this is something which is an advanced machine learning topic, so you will find it difficult to understand. So I'll suggest.
Himanshu, Gurpreet is asking if same metrics works for deep learning models also.
Yeah, Gurpreet, the same metrics can work for deep learning models also. So if you are talking about a classification in deep learning, right, the same metrics will work. So all these algorithms, Gurpreet, the log loss, or the ROC curve, or the confusion matrix, and different variants of the confusion matrix, they all work. So either you solve your problem from machine learning, simple data science problem, or deep learning, because these are to evaluate your model. So that doesn't change if you use different model or different techniques.
Any other
So do
question,
we?
guys? I'm not able to see any other questions here. Just 2 more minutes. Any other questions here? Or as I said, you can send it to contact@cellstrat.com and Himanshu will respond it. So next week's webinar, we will be announcing the topic in our Monday's newsletter, where also you'll get a recording of this webinar, and we'll try to upload it by day after tomorrow on YouTube. So, and you should keep a watch on our meetup page where you'll be able to see a regular meetup happening or being announced. So I think that's about it for today. Thank you guys. Hope to see you next week. Thanks. Bye.
Thanks all. Bye.